So I sent an email out that had the results for the exam for the class, right? And overall, I was pretty pleased with certain aspects of the exam, mainly that most of you were able to get the geometry of the revolution solids and things like that down. Still a little bit concerned about algebra, just like algebra skills stuff, but the way I graded it, I was really looking for the proper integrals in all the problems. I told you you could throw out one problem, right? Well, I wound up throwing out two. So what I did was, how many problems were there? There were 11. Okay, I counted number 11 as a bonus. So if you had thrown out number 11, then I went back to your test and I threw out the problem that you missed the most points on. And so everyone got 11 thrown out, but if you did part of it correctly, you would have got a bonus, something on it. So everything is out of 80 points possible, right? And then you add the bonus. So if I took off 10 points, you got 70 out of 80. You figure out what that is, and then you add the bonus to that. So if your bonus says +3, what I would do is, you understand what I'm saying? If I took off 10 points in the test, -2, -3, whatever, it's all -10, I subtracted that from 80, that would give you 70 points. Divide that by 80, that's your decimal grade, and then convert that to a percentage, and then add whatever your bonus was, 3 points. So if you have questions on how I computed it, you can ask me. We can talk about it, all right? But that's the way it was done. I'm not going to entertain any questions over it because I want you to just take it home, look at it. If you have any concerns about the way something was done or the way I took something, how much I took off for a certain problem, then please just get with me, all right? Anyone else need their exam? Okay, at this point you kind of know where you stand in the class. This is, we will not have another exam before the drop date. So if you feel like you're in a situation where you might want to drop the class, then you might want to talk to me about it. I forget how much each of our exams are worth, but we only have one more exam and then the final. So where you are now is a pretty good indication. You of course could move quite a bit from it, but if you're happy with your grade, content, fine. But if you're concerned, just get with me. All right. All right. Let's get down to business. Chapter 8. Sequences and series. So most of the time when you talk to people about Cal 2, you ask them, what's Cal 2 about? They all say, well, integration, right? All these techniques of integration. And they remember the solids of revolution most of the time, like, oh yeah, you revolve these things. And then they say sequences and series. That's the other big part of this course. So chapter 8 is going to take us a while to get through here. The topics are pretty, I think, intense because they require a different type of thinking than we've done before. I think. I mean, we'll see. We'll see how you handle it. But for most students, this is kind of brand new. Like most students maybe would, not most. There are some students that came out of high school, they've seen calculus. Like they've seen Cal 1 and Cal 2. Not many people come out of high school or have past experience with sequences and series. So it's kind of a brand new topic. That can be good in some ways because no one has like an advantage over you in that sense. So if you have any questions, if I do something and I assume you knew that, or you can extrapolate it from what I'm doing, just stop me, all right? Don't hesitate. Don't be like, oh, well, maybe I should have known that or something. Just stop me. I'm going to try and motivate what it is we're going to be doing in this chapter. There's a lot of different applications to what we're going to do, but let me just try and motivate the idea with a picture. And we'll have to build up to this later. Oh, you know what? Let's not start there. Let's start with something else. If you have a calculator, get your calculator out real quick. And what I'd like for you to do is make sure your, well, we won't do a trig function. Let's do e to the x. So what I'd like for you to do on your calculator is put in e to the first power. And tell me what your calculator gives you. Some of your calculators are real smart, and they're going to tell you, oh, it's e, and it's just going to put e there. So what I'm looking for is the decimal answer. So 2.718. Anybody's calculator go further than that? So 2818 after that. And then some go further, right? Well, e is an irrational number. It's like pi. It goes on forever. It never repeats itself, right? There's no pattern to it. And so when you tell your calculator, give me e, and it says 2.718, how is it determining that number? Like, it just knows what e is? No, there's an actual computation that your calculator is doing. Same thing, if you put pi into your calculator doesn't know what pi is, okay? It does a calculation. The only thing your calculator knows how to do are basically 4 arithmetic operations: addition, subtraction, multiplication, division. That's it, right? So somehow your calculator is using one of those 4 operations or a combination of those operations to be able to give you 2.718. So where that comes from is where this picture is going to lead us. So I'm going to come back to this, and I'm going to show you what your calculator is actually doing. So let's take a look here. I think I'll go straight to it here, right here. Can you all see this? If you graph e to the x, right? Here's e to the x right here. That's this red graph, right? And we plugged in 1, and when we plugged in 1, pull this up here. When we plugged in 1, we got 2 point something. It's like up here somewhere, right? Yes? Well, again, your calculator doesn't know what that e is. It can only do add, subtract, multiply, divide. So what I would like for you to look at is this line here. You see this black line? This black line, the equation of that line is in this top corner in black. See it? The equation of that line is 1. Does everyone agree that that is the function f of x equals 1? Yes? Okay, would you say that that black line is approximately e to the x? Yes or no? Look at the red curve, look at the black curve. Do they look like good estimates of each other? No, right? Okay, so what I want to do now is I'm going to change this function up here from 1 to 1 plus x. Now, is this better? It's dead on right here, isn't it? But over here it's not. It's off. Well, watch. I'm going to change it. Instead of being 1 plus x, and are y'all okay with the fact that this is a line 1 plus x? It's the identity moved up 1. Yes? So now I'm going to add something else to it up there. Right there. So now I'm leaving the dotted line behind. That dotted one is the one we had just a second ago. And now this black one is a parabola, right? It's this 1 plus x squared. Is that black curve getting better, getting closer to that e to the x? Yes? Now I'm going to add another one. Now this is a cubic function. Now I'm leaving that parabola behind again as a dotted curve. Now you see the cubic here? Third degree polynomial goes like this, then it curves up. Was that better than the quadratic we just had? Yes? Okay, I'm going to keep adding things. Now I have a 4th degree polynomial, which is this black one. Is that better? Yes? Okay, now I'm not going to do it one at a time. I'm just going to keep going faster and faster and faster. What's happening? Right? Yeah, it is wagging. Let me bring the x out like this, and I'll just keep adding more and more and more, and more and more and more and more. Right? So what's happening is that each of these polynomials is getting closer and closer to the e to the x, isn't it? And now to get way out here, I'd have to go a lot more. Now look at that polynomial. That's a 12th degree polynomial, isn't it? But what we're saying is that if I wanted to approximate what's happening at 2, right? What I could do is I could plug 2 into this. Now, could you do that by hand? You could. I mean, you would probably need your calculator though, right? And on a calculator, you could do this pretty easily. It would take you a little while to plug 2 in there, right? You plug 2 in right here, plug 2 in here, plug 2 in here. You do that, and you would get something, right? That's exactly what your calculator is doing. Your calculator knows this part of it, and it's just plugging 2 in, and then at some point, the program that your calculator is using says at some point when the next iteration I do, so if they go out, let's say they plug in 2 here, all the way through here, and they stop at 8, and the calculator says, okay, remember that number, now go here. If the difference between those two numbers is small enough, it says stop doing it, all right? And then that's what it returns to you, that decimal approximation. Does that make sense? So if you have your calculator out, what I'd like for you to do is I'd like for you to come in here. Let's just do those right there. So do one, what were we plugging in for x? It was e to the what power? 1. Okay, plug 1 in here. I said 2, didn't I? Did I say 2? Plug 1 in here. Plug 1 plus 1, and then do what? 1 squared over 1 is 1/2. And then do 1 cubed over 6, which is 1/6. Just do that, and what do you get? 2.6 something, 2.6666. Okay, that's close to 2.7, isn't it? But not close enough. So now add to that, what? 1 over 24. .708. It's even closer, right? Now add to that 1 over 20. I'm sorry, 1 over 120. Wake up. So you see we're starting to what we would say converge to the true value of E. And the further you go out, the closer. Now, is that a problem? Does anybody have a problem with that? I mean, E goes out forever and never repeats itself, right? How do we know that they keep changing? Well, because of this. I mean, this tells us every time I go out, it's changing, right? And so if you're building a shed and you're trying to get your dimensions right, you just got to be close, right? So how close? Well, for certain applications, you would maybe only need E to 2 decimal places. You're building an aircraft, right? You want your tolerances to be even better, so you want to go a little further, right? You're building like ball bearings, or what are those discs where they put all the microprocessors on them? What are those called? Like a wafer. You're doing wafers in a computer, building these microprocessors, right? You don't want to round to 1 decimal place, right? You're going out real far. So how far you go out is completely up to the application. The point is we can go as far as you need to go. We can get as close as you need to get. Does that make sense? Now here's a fascinating thing about this. If I'm telling you right now that e to the x is this right here, and it keeps going forever, okay? Keeps going. The further I go, the closer it gets. If that's the case, I would like to ask you real quick, what's the derivative of e to the x? Well, in Cal 1, it's e to the x, isn't it? Isn't it? Okay. So look at this right here. This is e to the x, right? Take its derivative. Now, how do we take a derivative of a bunch of things being added together? Term by term, right? Okay, what is the derivative of 1? 0. What's the derivative of x? 1. I'm going to put it right here. Okay, what's the derivative of x squared over 2? The 2 comes out, cancels, you get x. What's the derivative of x cubed over 6? So 3 comes out, x squared over 2. Right? And if you keep going, what are you going to get? Exactly what's up there. It is its own derivative. It's the only function that behaves that way, other than 0, other than the 0 function. Do you see that? That's quite remarkable, that we can actually, instead of actually having to differentiate that, we can differentiate this, which is much, not easier, but hell, it's the power rule, right? I mean, the power rule is the first derivative rule you use that you learn. Just drop the power and reduce the power by 1. So And what if you take the antiderivative? What's the antiderivative of 1? X. What's the antiderivative of x? 1/2 x squared, which is, well, did I write that? Jeez, man, I need to wake the hell up today. God. Right? And if you keep doing antiderivatives of each of those, you get the same thing, right? Do y'all follow that? So the question, this begs the question, can you do this with all functions? Can all functions be written as a, what do we call this? It's a series of powers of x, right? A series like a chain of things, right? A series of power functions, right? Each of these is a power of x, power of x, power. So this is a series of power functions. And so we start to say what functions that we've always known can be converted over to this power series representation. And then, what can we do with that, and how do they behave, et cetera, et cetera. And it turns out to be a theorem that says as long as the function is continuous, which means well-behaved, right, then you can always approximate it as close as you need to with a power series, no matter what it is. So our goal is going to be to try and look at functions, eventually take some function and represent it as its power series expansion. Got it? Okay. Now, I'll give you a couple of other visuals on this. Here's sine x. This one's kind of cool. I'll give you a couple of periods of sine here. Right now, I'm approximating the sine function with this, right? 0. That's not a very good approximation. There, that's a linear function, right? X, not very good. Quadratic should be better. Quadratic should be better. Why did it skip the quadratic? Oh, that's right, because it doesn't have a square. Sorry, my fault. Okay, the cubic is the next one. And then 4th degree doesn't have 5th, 6th, 7th, 8th. Look at that. Isn't that cool? Y'all see that? Okay. Now, does anybody notice something about these power functions? They're all the powers are what? Odd. Didn't we say sine was an odd function? It's not a coincidence. Cosine's even, right? So if you do the cosine one, every power function is going to be even. Here's one that's a little less, I guess that function isn't very intimidating to us because if we say plug in a number, we plug in a number, right? It's not that big of a deal. Like sine's a little mysterious. Like what's really happening in that sine function that spits out that answer, right? Or the e to the x, like what is that, what's really that e? 1 over 1 minus x is pretty clean. But again, we can convert it into a power series. So I'm approximating the red one here with the black one. By the way, this is a vertical asymptote. I forgot to tell the computer to take it out. So that line's not very good. That's better. Now look at what's happening here. This is going to come up later. We're going to notice something here. Later on, we're going to realize that when we do this power series thing, that there's sometimes that our approximations are really good. Like this one's really good, right? But there's something happening over here. Like it doesn't seem like I'm getting close over here, right? And what's happening is that within a certain range, my approximations are really good, aren't they? But outside that range, they don't work. And what we'll do is we'll call that the radius of convergence. And it's not a worry to us. We don't have to be too paranoid about it because what we'll do, I can show you in this example. I can't show you in this one. But imagine that this one was behaving the way the last one was. It was really good in here, but it wasn't very good out there, okay? Then all we have to do is what we call shift the center. So we shift it. Let me back this back out to like 2. Okay, so look. You see, now I'm at this point instead of at the origin. And if I do approximations here, damn it, I went too far. I moved my point there, put it there. So what will happen is all my approximations will be really good here. And do y'all follow what I'm saying there or not? It's a little, I might be pushing a little too hard. If I know I can get this power series to work, but only within a certain interval, then if I'm having trouble and I'm wanting to know what's going on out there, all I do is I shift my center over here, and I know I'm going to be good in there. And that's a Taylor series. It's what we call it. We shift it out. We move the center of where we're doing the approximation. So pretty cool stuff that you can do. Here's an example of a function, e to the negative x squared. It's a classic example because if you try to integrate e to the negative x squared by hand, there's no technique of integration that's going to work. So there is no antiderivative, capital F, that you'll ever be able to find that's a nice closed form. You know, like the antiderivative of x is 1/2 x squared. Nice. This, not going to happen. However, because we just saw a second ago in the previous example right here, we saw that I'm going to replace the x with u. E to the u would be 1 plus u squared over 2, right? Plus forever. Yes? If that's the pattern for e, then if I want to figure out what e to the negative x squared is, I replace all my u's with negative x squared. So it becomes 1 plus negative x squared, right? Which would be 1 minus x squared. There, see that? And then I replace this one with negative x squared, which would become positive x to the 4th, right? So that would be right here, right? Over 2. And notice what happened there on my picture. I'm trying to approximate that red thing, right? It's okay. Better, 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 right? This one actually, the radius of convergence here is infinite, which means this will converge no matter where you start from. So the more I go, the better I get, the closer it'll get. So if I wanted to integrate this, right, like if I'm trying to find the volume of something revolved around something, and this is the function I'm looking at, I can't find the antiderivative to do that. But what I could do is I could rewrite this right here as that. Yes? And then integrate each one term by term, and then get an answer. Now, I'd have to stop eventually, wouldn't I? But then that goes back to how, what do you want your tolerance to be? This is a very, very powerful method. This is the way computers work. Computers do not go sit there and, think about sine as being like opposite over hypotenuse. It has no idea. When your calculator is doing sine, it's doing this series right here. Okay? But we have to start somewhere, right? And I don't know why I just reopened the program I'm using. So where we're going to start is with this idea of sequences first. We can't get to series until we get our heads around the whole idea of just what a sequence is, the way they behave, different properties of sequences, notation, and then we'll start doing the series. So our first idea here is the definition of what we'll call a sequence. A sequence for us in this class is a list of numbers. It is possible to have a sequence of things that aren't numbers. You could have a sequence of functions. You could have a sequence of vectors. All sorts of things. But here, this class, sequence for us is just a list of numbers. And since they're a list of numbers, I have a first number, second number, third number, fourth number, right? The way I'll write them out is like this. A1, A2, A3. And then I keep going out, and this would be the nth number in the list, wouldn't it? Okay. If my sequence of numbers stops like this, so I have n numbers, then we say this is a finite sequence. It's finite because there's a finite number of numbers, right? If the sequence goes forever and I don't want to stop the list of numbers, then all I do is write like dot, dot, dot. Most of the time, 3 dots means forever, but I've always been just a little bit over-ambitious with my dots, and I just go like, you know, dot, 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 dot. So 3 dots is what most math people use for the idea of continue that pattern. Okay, this would be an infinite sequence. Can somebody give me an example of an infinite sequence of numbers? An infinite sequence of numbers. So you said pi, do you mean like each of the decimals represent each of the decimal points as a number? Then that would be okay, I agree, so that would be fine. E would be repeated. Okay, so you're looking at decimals. What I was thinking is something more like the integers. 1, 2, 3, 4, 5, and then including 0 and negative. That's an infinite list of numbers, isn't it? An example of a finite list of numbers would be the number of students in each building, in each classroom of this building right now, right? So like, you go to each class, take that number, next class, take that number, next class, right? That's going to be a sequence of numbers. And that sequence will be finite. Why? There's a finite number of classrooms in this building, right? So different type of sequence. If you take the Spurs last season, all their home games, the number of people that attended each game, that would be a sequence of numbers. It would be finite. Okay, so now what I want us to do is go back and think about a function. Okay, so recall the concept of a function. A function basically had, in a picture form, it had input and it had output, right? What you normally plugged into a function, things like f of x equals x squared, f of x is sine of x, right? These functions that we've been dealing with, we usually plugged in a real number, right? Just some number, r. So this double struck r means a real number. And then it does something to that number and spits out a number, doesn't it? And that number is usually a real number also. Agreed? That's what a function has always looked like to us. So one way we could have written that is, let's say we had a function f. I put a colon after it, and I write r, arrow, r. What I mean by that is I'm defining a function f that takes a real number in and spits a real number out. Goes from r to r. Make sense? That's what a function is. We can look at sequences like functions also. But the difference between a sequence and just our traditional version of a function is going to be illustrated in this example. All right, so let me show you this quick example. If I have the function f of x equals x squared, then most of us understand this to mean that you're going to take in a number and spit out a number, right? And I can put any number I want in, can't I? I can put in 0, I can put in 1, I can put in 0.5, I can put in negative 2.6. So what happens is if I go to a graph, I come in here, I plug 0 in, I get 0. If I plug in 1, I get 1, right? If I plug in 0.5, I get 1/4. And when you put all these things together, you draw the parabola, don't you? And you get this nice curve. And it's continuous, right? Meaning that I can draw it without picking up my pencil. It's connected. Everything in there is connected. Yes? Okay, that's because this function was taking a real number in and spitting a real number out. So the difference between that and a sequence is this. I can define now a new function, and I'm going to call it f, but I'm going to say f of n. Now I'm saying n instead of x to stress that I'm about to change my domain. I'm about to change what you're allowed to plug in. I'm still going to call it not x squared, but n squared. So this looks like the exact same thing, doesn't it? But this time I want you to know that this function goes from double struct z plus into r. Or you could have written n into r. So n being the natural numbers, which are the counting numbers. What are your counting numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Z, when you see that double struct z, that means integers. Now the integers are like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 forever. And then also integers include -1, -2, -3. So if I write z with the plus, that means only positive integers, which would mean 1, 2, 3, 4, 5, 6, 7. So the same, it would be the same thing as the natural numbers. Do y'all see that? So now what I'm doing is I'm restricting your domain. I'm telling you, you cannot just go throw any number into that. You can only throw in counting numbers, the natural counting numbers. So if I try and do a graph of this, can I plug 0 in? No. Can I plug in 1? Yes. If I plug in 1, I get out 1, don't I? If I plug in 2, can I plug in 2? Yes. And I get out, whatever, 4. Can I plug in 2.5? No. I can plug in 3, though, right? And so what I have here is the input, right, is 1. The output is that in, out. It's 1 can go in, 1 comes out. 2 goes in, 4 comes out. 3 goes in, 9 comes out. 4 goes in, 16 comes out, and so on and so forth, right? What does the graph of this look like, though? Is it a connected, nice, curved, continuous? I can draw it without picking up my pencil? I cannot, right? Because it's just a bunch of dots. And there's a bunch of space between them, right? Like between 1 and 2, there is no graph. Between 2 and 3, there is no graph. There's just a bunch of dots, isn't it? And if you look at this, the left side, like if I give you a different function, right? And I say, hey, look, for this new function, I'm going to give you like sine or whatever it is. I still restrict you to those, to the integers like that, the positive integers. Then wouldn't you agree if you drew a table, your left side would always stay the same? Right? Like this part's always going to be the same if I restrict you to the natural numbers. The only thing that's going to change is the right side. And that will depend on the function itself. This is what x squared looks like, right? If it's some other function, it's going to look like something else. Yes? So this right side is really what changes when we talk about fixing our integers over here, or our natural numbers here. This is really the only thing that's changing. So I could, if I want to, look at the outputs only and put them in a list. So a set of braces. Just the outputs would be what here? 1, 4, 9, 16, ... Close it off, right? That would be an infinite sequence, wouldn't it? That infinite sequence is determined by a function, specifically the function n squared, where n is restricted to the natural numbers. Do y'all see that? I can write the sequence out without having to actually write the function itself. You have to recognize the pattern. You have to know that when I plug 1 in, I get this. When I plug 2 in, I get that. When I plug 3 in, I get that. When I plug 4 in, I get that. But that's enough information for me to recover the function. Do you agree? So the way that we're going to write this is as follows. Are there any questions? I'm moving on. The notation we're going to use is this. If we're going to take a function and restrict it from the natural numbers into the real numbers, then we could write f of n equals something. Now, I want to give us an example. Well, I guess I could, yeah. That's the specific example, right, that I just gave you. But the new notation, we're going to, instead of write that, we're going to write this. A sub n equals n squared. So it's like instead of saying f of n, right, f of n, we could have said a of n, but instead we say a sub n equals n squared. Now, let me show you how this works. By looking at this, because of this notation, you have to realize I can only plug in my natural numbers. So let's plug in the first natural number, which would be 1, right? This is the way we write the sequence. Now, let's figure out what's the first number in the sequence. So I'm replacing n with 1. Just put 1 in here then, right? 1 squared is 1. Then what's a sub 2? 2 squared is 4, and so on and so forth, right? But do you see the change in notation? Yes? Here's some more notation. So far, I've told you that a sequence goes from these counting numbers into R, but it actually turns out that it doesn't have to go from the natural numbers. It doesn't have to be 1, 2, 3, 4. It could start somewhere else, and I would need to be able to tell you that. So that's why we have this other sort of notation. Let's say I wanted to let you know that I wanted you to do n squared, right? But I wanted you to start at 3. I would have to write it in a set of braces like this. I would put n equals 3, and up here I tell you where to stop. So I put infinity. So this is another notation for what we just did, except I'm starting at n equals 3 instead of n equals 1. So I guess the key point here is that if they don't tell you where n starts, assume it's 1. If you want to change where you start, you have to specify it. Now, I could have written also this a sub n equals n squared with n greater than or equal to 3. That's another way we could have written it. So these are two distinct ways of writing the exact same thing. Just trying to get us used to the way you write these things. You okay with that? N being greater than or equal to 3 implies that it never stops. And the fact that I'm using n and not x lets you know that I'm using integers as opposed to just every number. Okay, so like 3.5 is not allowed. What is the sequence we already did, right? We don't need to write out the list of sequences, or should we? All right, the last way you could write this is actually writing out the sequence itself. Now, this is going to be a little different because where is it going to start? Okay, so my first number in my sequence would be 9, then 16, then 25, then I keep going, right? So all of those are equivalent, okay? All of those are the same. If you wrote this, that's the same as writing this, which is basically the same as writing this. What we're going to have to do in this class is we're going to have to go from one to the other. We may start with this. We may need to go back to the sequence. We may start with the sequence and need to go to this. It just depends. How about this one? Give you another example. If I write down what's another way I could write that? Give me another way I could write that. A sub n equals 1 over n, or you could do n to the negative 1, yes? Do I need to say n greater than or equal to 1? I don't have to, okay, because it is starting at 1. If you wrote it down, if you put with n greater than or equal to 1, that's fine. You're overkill, though. You don't need that information. You assume it's 1 unless otherwise specified. Here it was 1, so I don't have to write it again. Okay? Now, let's look at this sequence of numbers. Let's do like the first 4 or 5 numbers. So you start out by plugging in 1. 1 over 1 is 1. You plug in 2, you get 1/2. You plug in 3, you get 1/3, and then you keep going, right? 1/4. And this is just going to continue that pattern forever. Is that a finite sequence or an infinite sequence? Infinite, right? You get the idea, right? Any questions on this? Let's take a look at some common sequences, ones that are going to come up a lot. And maybe you can help me. What I'm going to do is I'm going to list out the sequence, the list, and I want you to help come up with the formula A sub n. So here's our first example. How could I get you to list out 1, 2, 3 forever? What would your sequence be? A sub n equals what? What? I'm hearing just n, right? Because where do you start at? 1. So A sub 1 would be 1. A sub 2 would be 2. A sub 3 would be 3. Yes? Don't overcomplicate it on that one, right? It's just straightforward. That's how you would generate that. How about this? This one will be a little bit more challenging. N minus 3. Okay, so all you're doing is you're taking this sequence. Each one is going up by 1, right? Adding 1 each time. But instead of starting at 1, you want to start at negative 2. So you basically want to shift this sequence over by 3, right? Do you all agree? So all I have to do is take that sequence and subtract 3 from it. So I just do A sub n equals n minus 3. And the good news is that if you get a sequence, a formula for it, you can always check it, right? Just by plugging in the, starting with 1. If you plug in 1, 1 minus 3 is negative 2. Plug in 2, 2 minus 3 is negative 1. And it should generate your sequence. Yes? Anytime you want. You just have to specify it. Yeah. You can always assume 1, but you can change it too. I mean, see, the thing is, let me show you like this. Could I have done this? Could I have written this? Would that work for this? No. But what if I added this to it? Would it work now? Yes. Because now I'm telling you to start at 0, right? Saying start at 0. Now if you plug 0 in, you get negative 2. Now you go up to 1, you would get negative 1. See what I'm saying? But because we didn't write down what the condition on n here, we assumed it's 1. But you are free to change that n to whatever you want. But it has to be an integer, and it can even be negative. We don't usually do it, but it could even be negative. Did I answer your question or not? Okay. So if this is, I'm glad you brought this up, because look at this. This is the sequence of numbers, right? These are 2 different functions for it, right? So would you agree then since these don't look the same, they're not exactly the same, there is not a unique representation for every sequence? You may have different representations of the same sequence. This gives you the same thing as that does. They look different. Yes? And so when you're in a test or something like that, if you have a sequence and ask you to give me the actual, formula for it, we may have varying answers, which makes it suck to grade. But because I have to really check to see if it works or not. But, you can approach it different ways. Now we try and all stick to 1 for n equals 1. N starts at 1. We try and all kind of use that convention so that all of our formulas don't look different. Okay, so basically this just starts, these sequences right here just start counting numbers, right? Just count them. So how about this? What if I want you to create the even numbers? So I put a star next to this, evens. This one comes up. I want you to start creating the even numbers. Just the even numbers, I want you to start at 2. So A sub n would need to be 2n, right? 2 times n. What was n by itself? 1, 2, 3, 4, 5, right? I'm doubling that sequence. So if I double the sequence, if I double the sequence, it becomes 2, 4, 6, 8, right? I'm just doubling it all. So yes, that would work. All right, how about this? How about if I wanted to do -6, -4, -2, 0, stop, and stop at 0. Those are all even numbers, right? They keep going up by 2 each time. Add 2, add 2, add 2. But where am I starting? -6. So it's like this one. It keeps going up by 2. I don't want to start at 2. I want to start at -6. So I need to shift it by how much? Take away 8 to get to here, right? Take away 8, take away 8, take away 8. Thing is, I don't want to go forever. So it's going to be the 2n that I know gives me the evens, right? Then subtract 8 from that. That'll shift everything over by 8. I want n to start at 1, but I want it to stop where? Well, I want my sequence to stop at 0. That means my n has to stop at 4 and start at 1. Do y'all see that? So I would do it like this. It's this sequence formula with my n starting at 1 and ending at 4. This is like number games here, right? I mean, we're just, kind of see that? Some people pick up on this really, really quick, and other people get real lost with it real fast. So I can't ever predict who's going to pick it up and who's not. Pardon me? Yeah, this would be like the range of the function right here. That's what the sequence is actually the range of the function. And then that over there is the domain. Okay, how about this? That was evens, right? How would I create the odds? And let's start at 1. 1, 2, 3. 1, 3, 5, 7. Forever. Well, aren't the evens 2, 4, 6, 8, 10, 12, right? And aren't the odds always 1 less than the evens? So like if I start at 2 for even, to get to 1, I just subtract 1. If I'm at 4 for evens, I just subtract 1, I'm at 3. If I'm at 6, I subtract 1, I'm at 5. So shouldn't I just create the evens and shift it by 1 or subtract 1 from it? Yes? So 2n minus 1 would work, wouldn't it? Minus 1. Sorry, I was thinking ahead of what I'm going to put down next. That would create that list, wouldn't it? Now, if I wanted to force you to use this instead, could you still create that list? Yes? Where would your n have to start? At 0. So I would have to say with n greater than or equal to 0, because now what I'm doing is I don't want to plug 1 in first, because if I plug in 1, I'm going to get 3. So I started at 0, so that will give me the first number of the sequence to be 1. And then when I plug in 1, it'll give me the 3. And then so in that, what I did was I actually shifted the index or the domain, right, in order to create the same thing. Again, there's not a unique representation for a sequence. You can have different versions of it. All right. I feel like y'all are getting this. Is that okay to assume? Anyone have a question? 2 stars on this one because this one's important. I want to create a sequence. Oh, crap. Sorry. I got my signs off there. It's supposed to be negative 1, 1, 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 negative 1, 1. Remember, that means when I plug in 1, it spits out negative 1. When I plug in 2, it spits out positive 1. When I plug in 3, it spits out negative 1. 4 gives me positive. 5 gives me negative. Negative 1 to the n. So what we're using here is that property of negative 1 that it's cyclical, right? It keeps changing, but it keeps changing back and forth between 1 and negative 1 depending on the power you raise it to. If I raise negative 1 to an odd power, it stays negative 1. If I raise negative 1 to an even power, doesn't matter, right? As long as it's even, it's a positive 1. Do you all agree? So let's see. If I start at 1, negative 1 to the 1, it's negative 1. Then go to 2, negative 1 to the 2, positive 1. And so this will work, won't it? Yeah? What if I came in here and said, instead of that, I want you to start positive. Well, be careful because if power is negative, that means drop it down. We don't want to do that. Okay, I'm hearing one answer. Let's see. A sub n equals negative 1 to the what? N minus 1. So what's your thought process there? Yeah, so like we know that when we plug in 1, we want it to be even, don't we? Because we want our first one to be positive. So when we plug in 1, we want it to be even. So we shifted this back by 1 so that when I plug in 1, I get 0. 0 is even, right? 0 is an even number? Okay. And then now when I plug in 2, what happens? 2 minus 1 is 1. That'll give me my negative. Yes? Is that the only answer? Someone give me another one. Something else that would have worked. So where? Set what to that? Negative 1 just to the n, and then say n is greater than or equal to 0? Do you all agree that would work? Now start at 0. This is telling you now I want to start at 0. If I start at 0 and I leave it as n, not n minus 1, then I plug in 0, I get 1. I plug in 1, I get negative 1, right? And this will create the same thing. Can anyone think of another one? There you go. Good. That'll work. Why would that work? Because if I plug in 1, I'm going to get an even number, right? And when I plug in 2, I'm going to get an odd. Yes? In fact, I could have done negative 1 to the n plus what? Any odd number, right? Any odd number would have worked. I could, in fact, have done, let's see, n minus 1. We already got that. N plus 1, n plus 3, n plus 7. You with me on this? Now, there's something a little subtle that you may not have seen. I just want to kind of point out with this. We know what that one creates, right? That created negative 1, 1, negative 1, 1, negative 1, 1. And we wanted it to be this, right? So I wanted all my negatives to turn to positives, all my positives to turn to negatives. Couldn't I have just taken this sequence and multiplied it by negative 1? So I could have just done negative 1 to the n and just multiplied that times negative 1. Yeah? And that should have changed everything? Well, isn't that the same base, different exponents? And when you multiply two things that have the same base and two different exponents, You just rewrite the base and you add the exponents, don't you? Rewrite the base, add the exponents. This, and we just said this would have worked, right? As long as it was n plus an odd number, it would have worked. Okay. I think you're good. Next note. We need to discuss something here real quick that you may not have ever seen. You may have seen, I don't know. So that symbol right there, y'all seen that before? Unfortunately, statistics, some stats, no? Design, what? Wait, say it again. No, that's just N, damn it. It's N, right? That's not the way, that's the whole time I just thought they wanted me to yell it. No? Okay. Yes, it's called factorial. Okay, this is called n factorial, the way you say this. N factorial. All this is notation, okay? This is purely notation. When I say notation, it's kind of like, would I ever write this down? 3 times 3 times 3 times, and I want you to do that 1,027 times. Would I ever write that down like that? Like, you understand what I want you to do, right? 3 times 3, that many times. Instead of doing that, we have a more condensed notation, right? We just put, what, 3 to the 1,027. That is the notation that we use to represent repeated multiplication. Yes? Repeated multiplication, we use exponents. If you go even further back, right, way back, if I want to do 5 plus 5 plus 5 plus 5, and I want to do that, right, and let's say I want you to do that 9 times, I guess I could have written them all out. Instead of writing, you know, that, I could just say what? 9 times 5, right? So multiplication is a way of representing repeated addition. Exponents is a way of representing repeated multiplication. N factorial is a way of repeating a certain type of multiplication, or getting you to understand a certain type of multiplication, but in a way that's nice and condensed so you don't have to write it out. Okay? So here's what it is. N factorial, or factorial, means this. And I'm going to give you some examples, then we'll write the definition. If I write 5 factorial, what I want you to really do is 5, then subtract 1 from that, 4, then subtract 1 from that, and then subtract 1 from that, and then subtract 1 from that, until you get to 1, and when you get to 1, you stop. So 5 factorial means 5 times 4 times 3 times 2 times 1. And then that's just a number, you figure out what it is. I think it's 120. 4 factorial would mean, 4 times 3 times 2 times 1. 24. 3 factorial would mean 3 times 2 times 1, which is 6. 2 factorial would mean 2 times 1, which would be 2. 1 factorial would mean 1. And this is why I'm doing this. 0 factorial. That's what you'd think, right? It's 1. Okay, so look, I'm going to highlight this. 0 factorial is 1. And what we say here is by definition. Okay, what that means is that when we define this symbol, we can define it however we want, right? Like, I can come in here today and I can say, hey everyone, I was just sitting there drinking too much beer and I decided that I'm going to write 5 with 2 dots and then like a smiley face next to it, and I can make up my own meaning of what that is, right? Yes? Why not, right? Well, factorial, there's a definition. The definition is that it's this, but whenever you try and plug in 0, it's 1. That's the definition. That's the way we define it. Now, you cannot do negative factorials. Okay, so you can't take -1 factorial. Can't do -2 factorial. So this is only defined for n greater than or equal to 0. Integers. So here's the actual definition, more formal. N factorial means you start with n, right? Then you multiply it times what? 1 less than itself, right? Then multiply that times 1 less again, which would really be n minus 2. And then 1 less than that, which would be n minus 3. And you keep doing that pattern until you get down to what? 1. That makes sense? That's the definition of n factorial. Now, the condition is that n must be greater than or equal to 0. And of course, n is an element of the integers. Double struck capital Z. N is an integer. So you can't, it does not make sense to say 1/2 factorial. Okay? 1/2 factorial makes no sense, because you're not allowed to plug in a half. Okay? All right. With that definition, some properties. What would happen if I took n plus 1 factorial over n factorial and asked you what that was? Now, pay attention to the parentheses. They're not there just for fun, okay? That means whatever's in here, right, it's the factorial of that. Well, just write down what is n plus 1 factorial. Just what's the definition of n plus 1 factorial? You're going to start multiplying things, right? Right? That's what you're going to do? Multiplying. What's the first thing you're going to multiply? Whatever's in here, right? What's in there? N plus 1, right? Then what I do is the next one is that n plus 1, take 1 away. So it's just n. Then the next one, you take 1 away from this, which is n minus 1. You following? And you keep doing that, don't you? Now I'm just going to keep dotting that down until I get to times 1. Now, divide that by, what's n factorial? That's n times n minus 1, all the way down to what? 1. Do you see what happens? You get cancellation, right? This n cancel, this n minus 1, this one, and everything in here is going to cancel with everything in here all the way till you get to the 1s, right? And the only thing left is what? N plus 1. What does not happen, though, okay, is the factorial is not like a number you can distribute. So this was not like distribute through here and make it n factorial plus 1 factorial over n factorial. That is not right. All right? No go. All right, let's see. I'll do one more example and see if you can get this one. What if I have 2n minus 3 factorial over 2n plus 2 factorial? Don't let the 2n in front throw you off. 2 times n is just some integer. Subtract 3 is some integer. And then, from that you can do your factorial. And same thing with this. So the top one will be what's the first thing in there? 2n minus 3. And then the next one, subtract 1, 2n minus 4. And the next one, 2n minus 5. And you keep doing this, right, until you get down to 1. Now the bottom one, the first one is what? 2n plus 2. Then take 1 away, so 2n plus 1, and then just 2n, and then should I stop? Why not? Gotten where? You're trying to get to 2n minus 3? Because that's what's up here, right? And then everything after that will cancel. So I've got to keep going here. 2n minus 2, and then 2. Watch the way I write this. See if you agree with this. I'm going to put it in red because I want you to see if you agree with this. Could I write this now? 2n minus 3 factorial. See, I'm not writing on the bottom here dot, 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 dot down to 1, right? Because 2n minus 3 factorial means 2n minus 3 times 2n minus 4 times 2n minus 5 times 2n minus 6, all the way down to 1, right? So instead of having to write all that crap out again, I could have just done this, right? And do you see that that will cancel? Yes? This right here cancels with everything up there. Well, there's still 1 up there, isn't there? So your answer is 1 over this, right? 1 over all that crap down there. 1 over 2n plus 2, 2n plus 1, 2n minus 1, oops, 2n minus 2. That would be your answer. So I want to come back up here and just show you a different way I could have written this right here, this one. What is n plus 1 factorial mean again? It was this right here. Couldn't I have written that n plus 1 is the first one, right? And then it's what? N, and it keeps going, right? But n and it keeps going, I could have written as n factorial, couldn't I? So that factorial is only acting on this end. That factorial has nothing to do with this anymore. And n factorial keeps going. I don't need to write it. And then all over what? N factorial, and then they cancel straight away right there. So I could, if I was kind of getting used to this, I could have realized that this 2n plus 1 on the bottom is bigger than 2n minus 3. And I would have realized that I would have to just strip off a bunch of these until I get down to 2n minus 3. So I could have left 2n minus 3 factorial on top. Don't write anything else out, just 2n minus 3 factorial. And then on the bottom, just do it until I get to the 2n minus 3. Once I get there, factorial, and then cancel them. Yeah? All right, let's switch gears. I just want to make sure you are comfortable with that. Like multiplying down to 1? You wouldn't in general, but if someone gave you a specific number, it would. Now, yeah, there are some assumptions we're making here. Like on this problem right here, we'd have to guarantee that n would have to be greater than 2. Because if n were like, you couldn't start at 1 here, because you get a negative number in a factorial, you couldn't do it. So like, at the minimum, n would have to be 2 or greater for this to even make sense. But if we were given an n, then these would be hard numbers, and we would know when to stop, right? Yes? Okay. Okay, I want us to find the formula for each of the following. So now what I'm going to do is I'm going to give you a sequence again. I want to see if you can come up with a formula for it. These are going to be a little more challenging. Two fifths minus 4/25 over 6/125 dot, dot, dot. I hope that's enough for us to establish the formula. So let me share with you the way that I approach these. I try and do it kind of systematically. I first try and see if the sequence alternates signs. Back in our notes, remember I had highlighted, I put stars on these two, right? Double stars. I forgot to put double star here. And I also forgot to tell you what these are called. These are called alternating sequences. Why do you might want to make a note of that. These right here are called alternating. What we mean by alternating, we mean alternating signs. Right? These are alternating sequences. The signs alternate as you move through the sequence. So back here, when I'm looking at a sequence in general, I first check to see if it's alternating. If it is, I take care of that first. Because here I have a positive, then a negative, then a positive, then I'm assuming a negative would come next, then a positive, negative, right? So it is alternating, but it's alternating starting with a positive. How do I make a sequence start with positive, then become negative, then positive, then negative? What do I need in the actual formula for that to happen? I need -1 to be raised to the n-1 or +1 or +3, right? I mean, there's a bunch of different things I could have used. I'm going to do n+1. Do you all agree that would work? As far as just the sign, I mean, you almost have to imagine that there's a 1 in front here, that negative right there is really like a -1 in front of the 4, that there's a 1 in front of this. Do you all see what I'm saying? Like, I'm just imagining there's a 1 here. It's not going to change the 2 fifths. The -1's next to the 4. It's not going to change that. The positive 1's in front of that whole thing. So this alternating part of this should take care of my signs in the sequence. Yes? Now let's look at what else was there. And I like to, again, I try and focus on the numerator and denominator separately. So in the numerator, I notice that I have what? And forget the signs now, because you've already taken care of that, right? In the numerator, I have what? 2, 4, 6. So probably the next one's 8. This is my numerator. How do I create the sequence 2, 4, 6? 2n. So next to this, in my formula, I'm going to write 2n. And I've taken care of the sign in the numerator. Now the denominator. Close. This is 5, right? This is 25, which is 5 times 5. This is 125, which is 5 times 5 times 5. In other words, this is 5 to the first power. This is 5 squared. This is 5 cubed. So what's happening is, if I look at it that way, this is 5 to the first and 5 to the second and 5 to the third. Then I can look at it that the base is staying the same. The only thing that's changing is the exponent. And where does it start? 1, 2, 3, and that's the term. So 5 to the n? 5 to the n, not 5 times n, right? 5 to the n. That should create it. Do you follow my logic through that? And you can check it, can't you? Let's just check one of them. What's a sub 1 for us? Well, it's -1 to the 1 plus 1 times 2 times 1 over 5 to the 1. So -1 squared gives me a +1. 2, so that's 2 up top, and on the bottom is 5. So it worked the first time. Am I sure it's going to work? No, but do I feel better? Yes, that it worked at least once, right? You would have to check the next one. I mean, you wouldn't have to, but if you really were like kind of, I don't know if that's going to work, you just check the next one, right? Okay. All right? Let's try another one. Now, I'm going to write these a certain way on purpose. So if you like the way I approached it, then maybe you can help me by telling me what you're going to look at first. Alternating, okay, it starts off positive. Wasn't that just like our last one? So I need to put in here -1 and then n plus 1, n minus 1, n plus 7. Doesn't matter. I like the n plus 1. It's one of my favorites. That'll take care of the alternating. 2n again? Kind of boring. Why would I do this? Why would I give you the same damn problem? This one's a little more challenging to see. Anyone see it? That's 2 times 1. This is 2 times 3, right? This is, you could say it's what, 8 times 3. You could say it's 6 times 4. You could also say it's 2 times 3 times 4. Right? And this one is, what, 2 times 3 times 4 times 5. I was trying to get you to, I was hoping that the numbers 2, 6, 24, and 120 would ring a bell from here. 120, 24, 6, and 2. Right? I was hoping that that would make a little connection, but maybe now it does. No, because you don't have any 5s in here anywhere. Right? All the bottom is, well, what's 1 here? 1 is just 1, right? So when I plug in 1, I need to get 1. When I plug in 2, I need to get 2 times 1. When I plug in 3, I need to get 3 times 2 times 1. So that's just n factorial down there, isn't it? This is just n factorial. Right? Plug in 1, 1 factorial is 1. Plug in 2, you get 2 times 1, that's 2. Plug in 3, you get 3 times 2 times 1, which is 6. Do y'all see it? Okay. That would be the formula. Now, I said I wrote this a certain way just so we would see things, but what if I would have, like, simplified all those fractions first? You would have had 2, -1, 1, -1/3, 1/12, ... Negative, what? Second one? Oh, yeah, -2, thank you. I'm not sure I'd be able to recover the formula from that. I just wouldn't, I don't know if I would have enough information to feel good about recovering that formula. And I wouldn't start by thinking factorial on the bottom initially. Do y'all see the challenge here? I mean, this could be a lot of different things, couldn't it? And so there are limitations to how good we can get recovering a sequence. Plus, we could come up with a sequence that does a certain thing and another sequence that's different that does the same thing in the first maybe 4 terms, and then after that they're different. So even when you do recover the formula, you are hoping that the pattern you think it is continues, although it may not. Understand? But the bigger lesson here is just, how do we break these things down? How do I rewrite the pattern that I'm seeing in a way that I can manage it later? Understand? Let me go back to something here real quick. Kind of tell you what we're doing here. Look at this expansion here of e to the x. Forget the x's are even there. Okay? Forget the x's are there. Then we have, what are the numbers? 1, 1, right? 2, This would be 1/2, wouldn't it? 1/2. This would be 1/6, 1/24, 1/120th. What do those look like? It's factorial, right? So what if I said I just want you to create the sequence of the numbers, or the coefficients, right? How could you create these coefficients? It would just be 1 over n factorial. That'd be it, right? 1 over n factorial. 1 over n factorial. If I wrote this, if I defined a sequence this way, then it would generate the sequence 1 over 1, 1 over 2, 1 over 6, 1 over 24, and so on and so forth, right? Is that the sequence for e to the x? Hold on, yeah, there's something wrong. It's 1, 1/2. Go back to it real quick. It was 1, 1 again, right? 1, 1 again, then 1/2, then 1/6. So I would need another 1 out front, right? There you go. So what I need to do is start this where? At 0. Now, if I start this at 0 instead, now, sorry, that's that one. If I wanted to do it so it made the pattern of the e to the x thing, then it would need to start at 0. Because what's the definition of 1 over 0 factorial? 0 factorial is 1 by definition. So you would have 1, then you'd have 1 again, then you'd have your 1/2, 1/6, 1/20, 1/24, so on and so forth, right? In fact, look at the powers on x here. What are the powers on x for e to the x? This would be x to the 0, wouldn't it? Then x to the first, then to the second, then to the third. So I could even come up with a better formula that, check this out, I could say a sub n equals x to the n factorial down here with n greater than or equal to 0. Then if I said write those out, what would you get? So x to the 0 is 1 over 0 factorial is 1, and then you would get x to the first power, which would be x over 1 again. Then you would get x squared over 2, and then you would get x cubed over 6, and so you would get it, right? You would get all those pieces. And how do I tell you to add them up forever? How do I tell you I want you to add that to that to that to that, add them up? Well, we're getting ahead of ourselves, but I'm just kind of, again, trying to lead us into this. We'd use a sigma notation, summation. I'd want to start where? Well, I'd want to start my n at 0. Where do I want to stop it? Well, I never want to stop it. What is it that I'm adding up? X to the n over n factorial. This is the definition of e to the x. E to the x is this infinite sum. This is what we call the power series. This is the infinite series that represents that function. So what I'm focusing on right now today is every power series that we're going to deal with is going to have a list of numbers, coefficients, right? Even if I come up to this one, I have a list of coefficients. This one's easy. What are the coefficients here? 1, 1, 1, 1, 1, 1, 1, 1, right? It's just 1 the whole time. This one, I don't know why it went to decimals. I know why. I shifted it, yeah. Okay, look at the coefficients here. 1 over 1, 1 over 6, 1 over 120, right? And it's alternating, isn't it? Positive, negative, positive, negative. 6 and 120 should start making you think factorials here, right? 6 is 3 factorial. 120 is 5 factorial, isn't it? Crap. Maybe that is 7 factorial. It is. So this looks like it's x to the n, right, over n factorial, except the fact that we're skipping n's, aren't we? These are only odds. Okay, well, I'm getting ahead of myself, but we could do x to the 2n, and then like something like -1 would give us this first one, and then on the bottom something like n fact 2n minus 1 factorial. Okay, we're getting way too far ahead, but I'm just trying to get you to see what we're dealing with right now is just working on these numbers and how to rewrite the patterns into the condensed notation so that we can pop it into a series later. All right, we still have 15 minutes, and I have a lot to still talk about. So since we have a sequence now, the idea of a sequence is just a list of numbers, we can talk about what's called the limit of this sequence. A limit of a sequence. Okay, so if you're given a sequence a sub n, then if we write lim n goes to infinity of a sub n equals L, or another way we could write this, a sub n arrow to L. These both mean the exact same thing. So if I write this or I write this, what do I mean? They mean the same thing, but what does it mean though? So here's what it means. If we write that, then we mean as n gets large, a sub n gets closer and closer to L. We had the same exact idea with functions. Exactly the same idea. The only difference is that these are not functions, right? Like, they're not functions in terms of a nice continuous function where you can draw without picking up your pencil. But geometrically, it's basically the same thing. Here's a picture of what's happening. Let's say I go back to calculus, and I tell you, look at the function f of x is 1 over x. That's a continuous function, right? Can draw it without picking up my pencil, except at 0. But it would look something like this. What's the limit on that one as x goes to infinity? So what's the limit as x goes to infinity of 1 over x? That is 0, right? Because what's happening is the bottom's getting big, the top's is staying fixed, and it goes to 0. Well, the sequence a sub n equals 1 over n, even though it's not a continuous function, it's just a bunch of dots, it would follow the same pattern, right? At 1, it would be here. At 2, it would be at 1/2. At 3, it would be at 1/3, right? So whatever the original function is doing, right, the sequence is going to follow it, right, and do the same thing. So the idea of a limit makes sense. The further out we go, right, the closer we get to some point. I guess the main difference would be that most of the time with sequences, we're letting n go to infinity. Where in calculus, we could let x go to infinity, we could let x go to different places, and we were interested, like, what's happening at this asymptote here? When we're talking sequence, in terms of sequences, we're usually letting n go to infinity. That's the only limit we look at. Okay? So if the limit as n goes to infinity of a sub n exists, okay? If it exists. What do I mean by exist? It gives you a number, right? If you get an answer, numerical answer, like the one we just did, the answer would have been 0, wouldn't it? That sequence was going to 0. If we get a nice numerical answer, then we say a sub n converges. If the limit as n goes to infinity of a sub n does not exist, It is possible for a limit to not exist, right? In Cal 1, we used to say DNE does not exist. If you take a limit of your sequence and it doesn't exist, then we say the sequence diverges. So it's kind of the same language that we used when we were doing, remember the improper integrals? If like when we had infinity at the top and bottom or something of the integral, we'd say converge and diverge. It's kind of the same usage of, same words, they're just used in a different setting here, all right? Convergence and divergence is used a lot. So if the limit exists, converges. If it doesn't exist, it diverges. On page 429, there's a whole list of properties of limits of sequences. So like if you have two sequences added together, you can take the limit on both of them separately. So I encourage you to look at page 429. I'm not going to list them all out here for properties. One of the most important things for us, though, right now is that we can use a version of the squeeze theorem with sequences. And the squeeze theorem said, like, if you can stick back with functions, it said, if you always have a function between two other functions, and those two functions go to the same place, then the one in the middle has to also go to the same place. So that's what this says. If you have a sequence A sub n that's less than a sequence B sub n, that's less than or equal to a sequence C sub n, for n greater than or equal to some n naught, then if the limit, well, I'll write a different notation. If A sub n approaches L and C sub n approaches L, then what can you say? B sub n must approach L. I can show you this in a picture. Let's say that's L. That's some value on the y-axis. Okay? If we have a sequence, I'll label this sequence A sub n. Let's say A sub n starts here, starts coming up, keeps going up, starts going like this, comes back up, and then keeps coming, and then just starts to get closer and closer and closer and closer to L. We call this one right here A sub n. We all agree that this sequence converges to L from the picture. Now, over here, it's kind of going up and down. It's not close to L, but eventually, right, as I go out further to infinity, it's getting closer to L. So there's an A sub n. Let's say I have, you know what? Can we make that our C sub n instead? It'll make it easier for me to draw this. And bring my A sub n here. I know it's probably hard for you because you got the same color pen, but can you all see it? That. Doesn't matter what's happening to these in the beginning, right? In the beginning, they can waver around, but eventually they're both going to L. So at some point, this C sub n is bigger than the A sub n. Do y'all agree? This inequality will hold? That's why it's saying over here, n greater than n naught. That means there's some place eventually n naught, where once you go past n naught, the C sub n stays on top of the A sub n. That's what that first statement says. Does that make sense? And that your B sub n, also after this point, has to be smashed between those two. So let's say here's B sub n. Here we go. And then it's trying to move around here, but it always has to stay between those two. Always has to stay between those two. Always has to stay between those two. So whatever it's doing, eventually it's got to go between the two, and if those two go to L, then the one in the middle goes to L. That's terrible drawing. Do you understand the idea, though? There we go. Okay, so that's the squeeze theorem. We have another theorem. Yeah, I'm not even close. I still have another three or four pages of notes from this section. Let me give you this theorem because I think it'll be theorem. If the limit as n goes to infinity of the absolute value of A sub n equals 0, then the limit as n goes to infinity of A sub n must be 0. I'll show you a quick example of this. It's a great theorem. What if A sub n equals -1 to the n over n? What is this doing? Is it converging or not? Well, let's list out some of the terms of this thing. Plug in n is 1, and what do you get? -1. Plug in n is 2, you get 1/2. Plug in 3, you get -1/3, and so on and so forth, right? Is that getting closer and closer to a number? This right here, is it getting closer? It looks like 0, right? We could agree with that. Would you all agree with that? It looks right, but let's see how this little theorem works. It says, instead of looking at A sub n, look at its absolute value. What's the absolute value of A sub n? The absolute value of A sub n, that -1 is no longer a factor, is it? The absolute value of -1 is going to be just 1. So this is just 1 over n, right? I think we're all more comfortable with the idea that that goes to 0, right? So the alternating part of it doesn't factor in here. And this theorem says if that goes to 0, if the absolute value goes to 0, then I can guarantee you this one does. See how that works? Now be careful. Look at this example. Tell me about A sub n equals -1 to the n. What is that sequence doing? -1, 1, -1, 1. Keeps going, right? Is that converging? Doesn't make sense that it would, right? It's 1, and then the next time you go out, it's -1, then 1, and then -1, 1, and -1, 1, right? Keeps doing that. So can we apply the theorem that we just got? What's the absolute value of A sub n? That's just 1, right? And that sequence looks like this. 1, 1, 1, 1, right? Is that converging to what? 1. It's just 1, 1, 1, 1, 1, 1, 1 the whole time. So it is converging to 1. So I could say that this sequence right here, notice what I'm doing is When I say the absolute value of a sub n, when I draw this arrow to the side here, that really means I'm saying limit as n goes to infinity of the absolute value of a sub n equals 1. So we have to be a little careful with my arrows because this is kind of a different arrow than this one. It's just bad notation for me. This arrow meant that this means this, right? This means this. This arrow means that sequence converges to 1. I'll work on that. I need to not do it that way. Maybe just take those arrows out. That is that. That is that. So if the absolute value converges to 1, does that mean that the one up there went to 1? Is that what the theorem is saying? Yes? Careful. Go back and look at it. It says if it goes to 0, if it goes to 0, then the other one goes to 0. It's not saying that if the absolute value goes to something, then that one has to go to the same something. It only works if it's going to 0. So the reason why the theorem does not work here is because the absolute value does converge, but it goes to something other than 0. It goes to 1. So therefore, it doesn't tell you anything. This sequence diverges because it goes back and forth between two numbers. All right, I'm out of time. I'm sorry. I don't even know if I gave you enough. I doubt I gave you enough to really do a good part of the homework. So let me see what we've got in store. I was going to have you do 5 through 32 on page 434, but you can do 5 through 8. You can look at 5 through 8. 9 through 32 are all like what I did here, where I give you a sequence and you tell me if it converges or not. The problem is I haven't shown you the different methods that we use to attack these. And so you're very limited. So I would hate for you to go try those and run into some issues. So you kind of almost don't have homework other than like the first 4 problems out of there. But I would read maybe that reread that section or something. If you came in late, the tests are up here.